Hello everyone and welcome back. As you learned from the previous video, simulations provide hands-on practice with virtual or simulated equipment and procedures that would otherwise be too expensive, risky, or complicated to carry out in a traditional lab setting. When teaching STEM, engaging students and offering meaningful hands-on learning experiences is essential. Today, we'll look at the application of simulations through two practical examples. The first is a case study titled Impact of Augmented Reality Lessons on Students' STEM Interest, that explores embedding augmented reality simulations in authentic inquiry activities, focusing on medical surgery lessons for senior high school students in the process of selecting their university major. The project, including the use of simulators, resulted from a collaborative effort among scientists, electronic engineers, and medical doctors from the University of Science and Technology and the University Hospital, some of whom were directly involved in the experimentation. The initiative primarily aimed to inspire students to consider and pursue careers in STEM fields. Augmented reality was used to contextualize students' exploration of medical surgery. The researchers also investigated students' perceptions of these lessons and simulators and their interest in STEM. The participants took part in two specific augmented reality lessons, one on laparoscopic surgery and another on cardiac catheterization. These lessons were designed to integrate medical science, electronic engineering, and mathematics, reflecting the transdisciplinary nature of fields like biomedical engineering. The students interacted with computer-simulated experiments or equipment that combine authentic context with these simulated experiments, serving as a vehicle for manipulation and spatial visualization to achieve perceptions of the real world through interactions between physical and virtual environments. Students were organized into groups and provided with Android tablets to interact with physical surgery simulators by scanning QR codes. Each lesson presented an authentic clinical scenario where students role-played as surgical interns, diagnosing illnesses based on medical data, such as X-rays or electrocardiograms, and then performing procedures using the simulators. In the laparoscopic surgery lesson, students diagnosed a condition and operated a simulator using 2D images. In the cardiac catheterization lesson, they diagnosed heart issues and performed angioplasty on a simulator synchronized with a 3D heart model. Developed through collaboration among scientists, engineers, and medical doctors, the simulators combined sensors, circuit design, and programming. The goal was to let students gain medical knowledge, experience surgical technologies, practice procedures, and stimulate their interest in solving real-world medical challenges. The student survey showed positive perceptions of the EAR lessons and simulators, with high motivation and engagement. Students valued the chance to experience surgical procedures, expand their medical knowledge, and see the connection between medicine and engineering. Some suggested making simulators more realistic by adding sensor-connected models or VR technology. So how can we leverage these insights in a higher ed STEM context? Augmented reality can facilitate spatial visualization, helping students grasp challenging concepts in fields like anatomy, engineering design, chemistry, or physics. By allowing students to interact with virtual elements overlaid on their real environment, AR can make learning more dynamic and interesting. Embedding AR within authentic inquiry or problem-solving scenarios where students tackle real-world inspired tasks using AR tools makes the learning relevant and purposeful. Implementing augmented reality does not require build complex simulators. AR technology ranges from simple mobile apps that overlay information on the real world to more sophisticated platforms for building interactive simulations. You can start small with the readily available apps. A practical starting point involves identifying learning objectives where AR can support understanding or practice, selecting appropriate tools, and designing realistic task-based activities around real-world scenarios. AR adds value by enhancing visualization and providing meaningful practice opportunities. The second example is informed by the research presented in the article Can PhET Simulate Basic Electronics Circuits for Undergraduate Students, which specifically investigates PhET's capability for circuits. PhET is a simulator platform. It's free and it can be easily accessed online or downloaded and installed for offline use. It provides a highly interactive virtual environment for various STEM materials, including basic electronics. In this example, PhET simulates circuits like voltage dividers, series, and parallel resistors. Its high level of interactivity includes visualizing current flow and simulating component failures, making the learning experience more dynamic and realistic. PhET proves to be an effective educational tool, allowing students to validate theoretical concepts through visual cause-effect relationships. Beyond conceptual comprehension, it also supports laboratory preparation by offering a preview of expected outcomes and serving as a practical alternative when access to physical labs is limited or unavailable. The interactive environment helps develop both practical and cognitive skills, simulating hands-on practice through the assembly and manipulation of virtual components by dragging and dropping and collecting elements. Moreover, the direct observation of the effects of changing variables fosters deeper understanding and engagement. The operational limits of real-world gears are made visible through simulated malfunctions. For instance, components burning out when exposed to excessive voltage or current, adding dramatic effects. The rich, interactive, and exciting learning experience offered by simulations makes them ideally suited for integration into a wide range of university-level courses, where they can reinforce theoretical concepts, support preparation for hands-on practicum, and foster the development of essential problem-solving skills. In essence, PhET's interactive features like the ability to manipulate variables, observe immediate outcomes, and receive simulated feedback when components are stressed, make it an ideal virtual lab. Together, these elements create a hands-on environment that promotes active, exploratory, and self-directed learning, all at the heart of inquiry-based learning. In conclusion, we invite you to consider how simulations could open up new learning opportunities in your courses. We also encourage you to explore platforms like PhET and discover how their many resources can become an engaging and valuable part of your teaching practice. Thank you for watching.